Cleaning in place systems run every day in food, dairy, and pharmaceutical factories. But behind what looks like a simple PLC cleaning sequence, complex chemical and physical processes are actually taking place. In this project, I built a real-time cyber-physical digital twin that connects a PLC cleaning sequence with a physical-based simulation running in NVIDIA Isaac Sim. The goal is to better understand what actually happens during a caustic cleaning process. One fundamental question appears in many industrial cleaning systems. Why must a system be thoroughly rinsed after a caustic wash before introducing an acid wash? To explore this question, I built an experimental framework combining chemistry, thermal physics, PLC control, industrial networking, and real-time digital twin. In many industrial plants, CIP cycles follow a sequence of steps: pre-rinse, caustic wash, intermediate rinse, acid wash, and final rinse. During the caustic phase, sodium hydroxide dissolves organic residues such as fats and proteins. However, introducing an acid directly after a caustic wash will create unwanted chemical reactions. This is why the intermediate rinsing phase is essential. The system modeled here includes a process tank equipped with a steam heating jacket, dosing lines, and multiple control valves. Water and sodium hydroxide are injected into the tank during the cleaning phase. The steam jacket controls the temperature of the liquid, which greatly influences cleaning efficiency. At the chemical level, caustic cleaning works through alkaline hydrolysis. Sodium hydroxide reacts with organic compounds such as fatty acids and proteins, breaking modular bonds and transforming residues into soluble compounds. Temperature is a critical factor for cleaning efficiency, but it's often oversimplified in simulations. In this model, the heating behaviors is described by a real heating transfer equations. As you can see, the rate of temperature increase isn't linear. It depends on the heating transfer coefficients, the exchange surface, and the thermal mass. In other words, the liquid does not heat up instantly. This gives digital twin a realistic thermal inertia. This is crucial because our PLC logic isn't just running on a timer. It's actually monitoring this simulated sensor, waiting for the process to react the required temperature before triggering the next step of the CIP sequence. To estimate how much cleaning solution enters the tank, the simulation models droplets as particles. In Isaac Sim, each drop is not just a visual element. It represents a physical entity with a defined volume and density. The mass of each particle is computed using a simple physical relation: mass equal to phi multiplied by the volume. By accumulating the mass of each generated particle, the simulation computes the total injected mass in real time. This is the moment where the simulation moves beyond visualization and becomes a physics-based model of the process. The cleaning sequence is implemented in the PLC using a step-based control logic. Step 10, water dosing. Step 20, sodium hydroxide dosing. In Step 30, heating and recirculation. In Step 40, caustic wash. Step 50, end of caustic phase. Transitions between these steps depend on measurements such as liquid level and temperature. In a real plant, these measurements come from sensors. In this experiment, they are generated by the digital twin. The process is simulated inside NVIDIA Isaac Sim. The digital twin is built using an OOIDT architecture, Object-Oriented Industrial Digital Twin. Instead of modeling each asset independently, reusable industrial objects are created. For example, a single valve object is created in the simulation. This object defines the valve behavior and can then be instantiated multiple times across the system. Multiple valves in the plant are therefore derived from the same object, which improve modularity and scalability. Inside the digital twin, some nodes read commands from the PLC, such as valve states. Other nodes write simulated sensor value back to the PLC: tank level, injected mass, temperature. From the PLC perspective, the digital twin behaves exactly like a real industrial process. To verify the communication between the PLC and the digital twin, I monitored the network traffic using Wireshark. The communication follows the typical industrial stack: Ethernet, IP, TCP, Ethernet, IP. One important detail here is the TCP port used by the communication. Port 44818 is the standard port used by Ethernet IP, the industrial protocol used by Rockwell PLC. In a perfect world, the network will be completely transparent. But here, we can see TCP retransmission occurring on port 44818. Even in virtual environment, network jitter can occur. Understanding these behaviors is important when synchronizing PLC logic with a real-time digital twin. When all layers are connected, we obtain a cyber-physical system. PLC logic, control commands, digital twin physics, simulated sensors, PLC decisions. The PLC executes deterministic control logic. The digital twin simulates the physics of the process. The simulated sensor feeds measurements back to the PLC. The PLC then adapts its control actions accordingly. This experiment demonstrates how chemistry, thermal physics, industrial automation, and OT networking can converge inside a high-fidelity digital twin. Instead of creating cleaning process as a fixed recipe, engineers can analyze the underlying physics and chemistry. If you are interested in industrial digital twins, cyber physical systems, and advanced automation architectures, consider subscribing to follow future experiments from Industrial Tech.